So far, all of the KEQ expressions that we've created and that you may have practiced with have used concentrations. So instead of just listing this with a KEQ, I will now, in as many cases as possible, list this as a KC to indicate that we're using concentrations. If you have something that is all gases, though, we could use pressures. So you'll see a KP listed for anything where partial pressures can be used. And obviously, let's do an example. So 2SO3 gas in equilibrium with 2SO2 gas and O2 gas, we could, as we have always done, write this with concentrations, and that would be the concentration of SO2 squared times the concentration of O2 divided by the concentration of SO3 squared. But this uses all concentrations, and we have pressures, so it would be nice if we could use pressure values. The format of the equilibrium constant doesn't change when you do this. So it's still the pressure of SO2 squared times the pressure of O2 divided by the pressure of SO3 squared. And you'll see that I have parentheses around these, and you should put parentheses around the P and then the compound or the element so that we can tell exactly what's being squared, cubed, etc., and what we're doing the pressure of. Now, what's super important is that these are not numerically equal to each other. So they're expressing the same thing, but we're putting in very different types of values with different units, so we need a conversion. Assuming that everything behaves as an ideal gas, which is the goal, given that we need an equation to do some calculations here. It'd be nice if there were ideal gases to make this a little bit easier. If that is the case, then Kp is equal to Kc times, in parentheses, so RT is in parentheses, and RT and RT only is to the delta N power, where delta N is the change in the number of moles of gas. So this really means add up the coefficients for the products and subtract the sum of the coefficients for the reactants. So in the case of this reaction that we're looking at, my product C plus D is 2 plus 1. We're going to add 2 moles of SO2 and 1 mole of O2. And I'm going to subtract 2 because I only had one reactant with a coefficient of 2. So my delta N is equal to 1. Okay. Now, if my delta N is equal to 1, I will have a numerical difference, but can you think of a case where my Kp and my Kc would be equal to each other? Okay. Now, we have been putting things now with different units into our KEQ expression, but we haven't given a unit to KEQ, and it doesn't have any. So we should talk about why KEQ has no units. This applies to Kc and Kp. So the concentrations and the pressures that go into this expression, they're expressed relative to a standard. So a 1 molar standard or a 1 atmosphere standard. And that means that the units are canceled out before we even do the calculation. So as an example, if our concentration of NO2 in a reaction was 1.5 molar, in the Kc expression, what we're really putting in for the concentration of NO2 is 1.5 molar referenced against 1 molar. So the units cancel out. So we're canceling the units before we put the values in, so what we get is something unitless when it is an equilibrium constant. We also have not dealt with solids or pure liquids. The concentrations of solids and pure liquids, well, pure solids, pure liquids, really anything that has an S or an L in your equation, they're not included. Now, this is because their concentrations are essentially constant, and the way that you will see this presented in a lot of textbooks is that you do initially include everything from a reaction But what we're really plotting in this equilibrium constant expression is the activity of the components of the reaction. And because the concentrations of pure solids and pure liquids are essentially constant, the activity of those things is 1. So they fall out of the equation. They don't contribute to the equilibrium constant. So the way that we will deal with this in our equilibrium constant expressions is by just leaving them out. So of course we should look at an example or two. If calcium carbonate is in equilibrium with calcium oxide and O2, where the calcium carbonate and calcium oxide are both solids, my equilibrium constant expression is just the pressure of O2. That's it. There is nothing else. In products over reactants, the product pressure of O2 coefficient is 1, so it's to the first power. The other product is a solid, it doesn't go in. And then in the denominator, the reactant doesn't go in. So this would all just be over 1, and we could leave it as is. So another example, Fe2O3 solid plus 3CO gas in equilibrium with Fe solid and 3CO2 gas. The products over reactants, I have solid on both sides, but I also have gas on both sides. I could express this in pressures, or I could express it in concentrations. I have the concentrations here. So on the product side, it's only the CO2. So it's the concentration of CO2 to the third power. And on the reactant side, it's only the concentration of carbon monoxide. So it's CO to the third power.